So now how we will relate the diffraction and the interference. As we know, diffraction, if we have a small gap, and when the wavelength is approximately equals to gap size, we have a maximum diffraction, and the wavelength is smaller than the gap size, we have a minimum diffraction. Less it will spread out. And different diffraction patterns are shown. As you can see, in this case, it is exactly equal. In this one, it's the wavelength is there and the gap size a bit bigger, and this is much larger. Now, changing like the distance between the slit, this is a Young's double slit experiment. The Young's double slit experiment is used to observe the diffraction. As you can see here in this pattern, that when the light is passing through the slit, it is spread out. When it's spread out, we call that the spreading of a wave, we call that as a diffraction. But when the light is passing through a single slit, that is what happened. But what we have a double slit. So if you have a two slits, this is a Young's double slit experiment. You have to learn the formula for this as well as the explanation for the Young's double slit experiment. So let's take we have the Young's double slit experiment. What happened in a Young's double slit experiment? Like we have two slits which are separated by distance. We have two slits which are separated by distance A. A is the distance between the two slits. And we have the screen, which is placed here. This is a screen. And we are observing a point X, or we are observing a point A. And this is a center where we'll have a central maxima. Okay, the dotted line is representing the center. The distance from the central maxima to a point where we are observing the pattern, we call that as X. So like example, any interference we are observing, constructive or destructive interference, we call this distance as X. The position where you're observing the interference from the center. The distance between the slit and the screen, some books they use the letter L, some books they use D, both are acceptable. So you can use the term L or you can also use the term D. So D is actually a distance between the slit and the screen. And this is the screen here. So what will happen as a wave will travel and they will meet at a point. When they meet at this point, we will have a maxima. The central maxima is there and the path difference will be zero wavelength. And there will be a constructive interference happen or occur. So the formula which relate the wavelength of a wave which we use and the spacing between the slits and the distance from the central maxima to the point where we are observing, that formula is the wavelength of a wave which is used here is equals to AX divided by D. This is the formula you have to memorize. The wavelength of a wave which is used in this purpose is equals to A, the spacing between the slits, X, the distance from a central maxima to a point where we are observing the pattern. It can be maxima or minima, but usually we observe the same pattern. So if maxima to maxima, and D or L is the distance between the screen and the slits. What is the use of A? Like how this is related? How? No, that will be given in the question. Like A can be any point, this point A, it can be any point where we are observing a pattern, like a distance. So in a Young's double slit experiment, it uses first what will happen, the wave will diffract as the wave is passing through the gap, it diffract. And these two diffracted wave will meet on the screen at different point on the screen, and it will result in a formation of a maximus and the minima. What about usually, what about A? A is actually what you can take. A, you can take a distance between the two successive maximas or two successive minimas. You can also take that. But usually we take as a maximal example, say this is maxima and there's another maxima. Okay. So A is a new maxima from the central maxima. What is the first maxima? We can call that as A. Or A is actually a distance between the two successive maximas or two successive minimas. You can also take, like, we have maxima, then we will have a minima, then we'll have a maxima, and then again minima. Same way, we'll have maxima, then we'll have minima, and then again we'll have a maxima. So what is X? X is actually representing the width of the fringe or the spacing between the two successive maximas or two successive minimas. Like it's a distance between the adjacent maximas, you can also say. Like one maxima to another, that you can say X. So the formula which relate lambda is equals to AX divided by D. So this X depends, for example, if I use a longer wavelength, is it clear? The formula and the labels? Anyone having a doubt or a question? So if I want to relate this space between the fringes with every other parameter, so I can say lambda into T divided by A is equals to X. So if I use a longer wavelength, what will happen to X? Will it increase or decrease? If I use a longer wavelength, what will happen to the distance between the two central two maximas, adjacent maximas? So that will increase as well. Like if a longer wavelength, if this is one maxima, the central maxima, so the next maxima will be higher. So increasing a wavelength will increase the spacing between the fringes. If I increase the distance between the screen and the slit, if this distance is increased between the slit and the screen, what will happen? What will happen to the spacing between the maximas? The spacing between the maximas will also increase. Because D is a distance, D, as you can see, it is a numerator, so both are in numerator. So if the value of a D is increasing, the value of the X will also increase. And it is obvious, like as you can see, if I'm observing the slits, like this is a screen and another screen is placed here, and we have the two slits, and say these are the maximas, the central maxima and then the adjacent maxima. So if the distance of the slit is increased from the screen, like the distance between the screen and the slit increase, that spacing between the maximas will also increase. Like this is a smaller distance, this one is a larger distance. So the value of the X will increase, as we have a formula that lambda is equals to AX divided by D, or lambda into D divided by A is equals to X. So both are in numerator, so if the value of a D is increasing, X will also increase. And if we reduce the spacing between the slits, like if we have a smaller spacing between the slits, what will happen to X? This was A here and this is A here. So if you use a smaller spacing between the slits, the value of the X will also increase. Like the X is the distance between the two adjacent fringes or the lines. So what is, in short, the Young's double slit experiment? So Young's double slit experiment, what he did, he observed the interference of the wave and he used a light wave. So in the Young's double slit experiment, this experimental setup, what he did, he took two slits and he used a coherent source, a monochromatic light and a coherent source. So what happened? When the light passes through first slit, it spread. When the light passes through second slit, also spread like diffraction. And he placed the screen and he observed the interference pattern. What he observed? He observed the maximas and the minimas. Like this representing the minimas. So here the center, at the center he observed a maxima. Then he observed minima, then maxima, then minima, then maxima, and then minima, and so on. This will be minima, then maxima, then minima, then maxima, and so on. So he derived a formula to show a relation between the spacing between the two fringes, the adjacent maximas, and he called this distance as x. From the central, always from central maxima to the maximum, the next adjacent point, the distance between the two fringes, he called x. The distance between the two slits, that is a. The distance between the slits and the screen, that is, it can be L, it can be D. Some books they use L, some books they use D. So both are acceptable. So how he relate all of them, that the wavelength of a wave which is used is actually equals to AX divided by D. So this is a formula which you have to learn. Like I will give an example. Say he observed a light which was having a wavelength of 590 nanometers. Okay. And the interference pattern is observed on the screen, which is 1.5 meter away from the slits. And the student observed the fringes, the 12 fringes, over a distance of 2.1 centimeter. We have to calculate the separation of this slits. So if you want to calculate the separation of the slits, first, what is the lambda here? What wavelength he used? 500 and so wavelength or the lambda which is used, that is equals to 590 nanometers. So 590 into 10 to the power minus 9 meter. So we have the wavelength. The screen, the distance, the D is given here, which is 1.5 meter. So we have D as well. 12 fringes, he observed 12 fringes, like he observed 12 lines. You can also take X as a fringe spacing, or you can also take X as a width of or the size of one fringe. Both will work. So if 12 fringes are there over distance of 2 points, like 12 lines are there, 12 fringes are there over distance of 2.1 centimeter. What is the spacing or what is the length of this fringe? So how I can work out the length of the fringe? So it will be 2.1 divided by 12. That will give us the value for X. Because 2.1 centimeter is a interference. He measured the 12 interference fringes, like 12 fringes which are spread over a distance of 2.1. So if we need for 1, so it will be divided by 12. So we got 0.175, but that is in centimeter. So we have to convert into meter. So we divide it by 100. So it will be 0.175 into 10 to the power minus 2 meter, or 1.75 exponent minus 3. So that is a value for x. So we got the value for x. We just need a. So just substitute, like lambda is 590 into 10 to the power minus 9. A is a spacing between the slits. X we work out, which will go there in division. That is 0.175 exponent minus 2. And the d is a distance that is divided. Other side will be multiplied, which is 1.5. So what is the value for A? The spacing between the slits. What is the spacing between the two slits? Okay, it is 5.1 into 10 to the power minus 4 meter. So that is the space between the two slits. So the Young's double slit experiment, what he did, he used two slits and the light wave diffract and produce an interference pattern where x is representing the distance between the adjacent bright fringes, when lambda is a wavelength, d is a space, the length or the distance between the slits and the screen, and a is a spacing between the slits. What is the part difference at the central maxima? What is the part difference here at this point? So what is the part difference? The central maxima. Good. That's a zero wavelength. What is the part difference of the first minima? Half of wavelength. What is the part difference of the first maxima? One wavelength. Same way, 0.5 wavelength or lambda by 2, and then there will be lambda. Is it clear? The Young's double slit experiment. Anyone having a doubt or a question in this?